All right, people, let's go ahead and get started here. So, today we transition out of the sort of, hey, let's learn a bunch of vocabulary and nomenclature stuff, naming things. We're going to start to get into the why. Okay? So, if you remember, I was talking about the what, right? Everything I was telling you about the periodic table and the charges, these are all what. Like these things do this. Here's how we name them. We want to now begin to get into the why does all this stuff happen, okay? And to do that, we need to really start to understand what's going on with the electrons inside of the atoms, okay? So if you'll remember, last week I left off, we had protons, neutrons, and electrons inside the atom. Rutherford, we started with the nucleus. We have protons and neutrons in the nucleus. We have electrons arranged around that, fairly far away from the nucleus in terms of total size of the atom somehow. But nobody knows exactly what's going on there. The classic sort of thinking is the electrons are sort of orbiting around the nucleus like little planets, okay? So this story takes us to sort of the end of the 1800s, early 1900s. A whole bunch of scientists, names that you have heard before, are working on this problem of trying to figure out how are the electrons arranged inside of an atom, all right? So the key thing that we find to probe and understand how the electrons are arranged, we need to understand and talk a little bit about how light behaves, okay? And so this is the time frame where our understanding of light is really developing and changing. We have these wonderful equations from a guy named Maxwell about how light behaves as a wave, okay? So we know that from Newton all the way back to Newton, we have these ideas about light and understanding how light behaves. There's a lot of debate. Is light corpuscular? Does it act as little particles? Or is it a wave phenomenon? And at this point in time, it's pretty settled. Light is a wave. It diffracts when it goes through tiny holes. And you get this sort of interference pattern that is a classic behavior of waves. We talk about and define waves by two key characteristics. We talk about their wavelength, how long distance-wise is it from the start of one cycle of the wave to the start of the next cycle, all right? So that's our wavelength. And we talk about the frequency. How often does a wave pass a given point, okay? Those two combine to give you the speed of the wave. And so we have the speed of light, c. We can therefore relate the wavelength and the frequency to that speed of light. This equation is on the useful equation sheet. It's one of three equations in the atomic structure section, okay? We're going to have to do calculations with this. The speed of light is a constant value. It's given on the useful equation sheet, 2.998 times 10 to the 8th meters per second. And that's printed on your useful equation sheet. So it's not like something you have to memorize. Wavelength will be a distance in meters, and the frequency will be a number in hertz, or 1/seconds per second. We're going to have to do calculations. So problems will say if the wavelength is this, what's the frequency? The one thing you got to watch out for is most of the time for visible light, the light that we can detect with our eyeballs, the wavelengths are given in nanometers, all right? But to do the speed of light, you usually have to convert that to meters. So we're going to do some metric conversion stuff like we did last unit using nano to meter conversion. Again, that's nicely printed on your useful equation sheet these days. Lots of great evidence for this in our everyday lives. The main one that you might see all over the place is what's known as thin layer interference. In thin layer interference, light hits a thin film like soap or oil on top of water. And because of the way that the light interacts with those interface between the soap and the water, you get a bounce back, okay, a refraction of the light. And so you get this kind of colorful bubble effect, right? This is only possible if light behaves as a wave. Particles don't do this, okay? Only waves react and bend and interfere at different places at different wavelengths like this. All right, so tons of evidence. Everybody's like, yeah, absolutely, light's a wave. Totally good. We've got it. We've got great equations to describe how it behaves. Okay, so where does the problem come in? So first step, waves are energy traveling through some medium. Okay, sound waves that you're all listening to right now. My diaphragm pushes air into my vocal cords, which vibrate, and that creates a pressure wave. So pressure causing the air molecules to vibrate back and forth travels through the air. Okay, water waves go down to the beach. You have waves breaking on the shore. You look out and there's this continual pattern of waves. That's energy moving through the water. There's a medium that the wave is traveling through. And that medium defines a bunch of things about how the wave behaves, how fast it transmits, all kinds of functions and things like that. Earthquake waves, right? A wave of energy passing through the earth. There's a medium. And so everybody's like, hey, let's find the medium that light is traveling through, because it's a wave and waves are energy traveling through some medium. So they're looking for what they call the luminous ether. And two American chemists in particular, Michelson and Morley, these two guys are really sort of important. They're sort of key guys for what's happening in this sort of area. They're American physicists, and they're studying what's taking place. And they build a device, an interferometer it's called, where they take light and they split it and make it travel down two different arms and then come back. And they look at the interference pattern of how the light interacts. So Michelson and Morley, what would they have? They have this setup here where they have the light, it's a beam splitter, they travels down, and what they're looking for is changes to this interference pattern based on the orientation of this device to how the earth is traveling around the sun, right? So if you are traveling with the medium, you get a different speed for your waves than if you're traveling across the medium. Sort of like when you're in an airplane and the wind is behind you, you can go, your plane is airspeed relative to the air is the same, 500 miles an hour or whatnot. But if you're traveling into the wind, you slow down because the wind is pushing you back. If you're traveling with the wind, your real speed over the ground is faster because the wind's carrying you along. Same thing should happen here, okay? And so they set this device up. It's exquisitely sensitive. It should pick up really tiny changes to the speed of light, okay? So tiny that they have problems calibrating this because trucks are driving by, people are walking down the hallway, and it's causing vibrations that are messing up their measurements, okay? So what they do is they set it on a giant block of granite because they want it to be super stable. And then they isolate that block of granite from the rest of the building by floating it on a pool of mercury. Okay, so this circle down here that's kind of looks a little shiny, that's mercury. And they've taken this block of granite and floating it in the mercury so that there's no vibrations from the environment around them. Uh, Elemental mercury is not super bad for you. Don't eat it. Mercury vapor, real bad for you. So as long as you don't heat it up, it's not terribly bad. So yeah, they spend decades making measurements and they find nothing. And for a long, long time, they themselves had trouble reconciling their null result with what's going on. And it took a lot of time for physicists to accept that light is fundamentally different than all the other waves. That light is an interactive phenomenon between electric and magnetic fields. And that what light actually is a self-propagating wave. It's energy traveling through nothing, through the vacuum, energy traveling in the electric and magnetic fields that permeate space-time. Okay? So we reset sort of everything about light. And the equations that take place are all now based on light being not traveling through a medium, being in the electric and magnetic fields. There's a lot of cool math that goes behind this. Really solid foundation. Now we get to the point where we start to talk about how does light interact with matter, all right? And so when light hits a piece of matter, it gets absorbed, the piece of matter gains energy, okay? And we can do the reverse. If I take a piece of matter and I heat it up, it emits light, okay? This type of light from objects that are hot is called black body radiation, okay? And so there is a really well-defined spectra that you can measure over and over for all kinds of objects of what color of light do you get when you heat up an object. And the problem that everybody runs into real quick is that if you use these wonderful equations we have for light and you calculate what you should get, it doesn't match the experimental result of, hey, I took this object and I actually heated it up, okay? So classical theory, this is what the equations for light say should happen, okay? And what you see is as you increase the temperature, where the energy is emitted should very quickly turn into ultraviolet light. It's known as the ultraviolet catastrophe. And objects should emit basically almost just pure ultraviolet light. This is what actually happens. You have an object at 5,000 kelvins, okay? The prediction of classical mechanics is ultraviolet all over the place. The reality is it peaks in the visible and you get very little ultraviolet. You have this longer tail in the lower energy frequencies, okay? So yeah, you don't get the ultraviolet catastrophe. Things don't spew out ultraviolet light at the exclusion of almost all other frequencies, which is what classical mechanics predicts, okay? So this is a big problem. And lots of people, physicists around the world, are trying to reconcile what's actually happening to what all the best classical predictions say should happen. Okay? And in desperation, a guy named Max Planck, a German physicist, he comes up with and has a crazy idea. And he admits in his papers, this is a crazy idea. I have no idea why it works. But if you do this one weird math trick, we can convert classical to match reality. Okay? So Planck's idea is, hey, what if we just arbitrarily cut off what energy light can have. And so Planck says what we have to do is move away from this concept of light as a continuous wave with infinitely dividable energies. Remember when we talked about atoms and we said, hey, we could talk about it as continuous, or we could start saying, no, there's a smallest piece. What Planck functionally comes up with is there's a smallest piece of energy. And mathematically, he works out if we limit the energy to having this minimum size, known as Planck's constant, then the classical stuff we're doing ends up matching the reality. In fact, that's how they figure out Planck's constant. They say, what does this value have to be to make the classical equal partition theorem match reality? And it turns out that this shows up all over the place. That there apparently is a smallest you can have in the universe. Okay? And that smallest you can have is measured by Planck's constant. And so what Planck does is he is said to quantize the light. So like we sort of said with atoms, they come in individual atoms. There's a smallest piece. That same idea happens to light. That the energy that a particle of light, which is a weird concept we'll talk about in a few minutes, could have must be Planck's constant times its frequency. And this equation is also on the useful equation sheet, and you're going to have to do calculations with it. Okay? So the energy of a smallest chunk of light is Planck's constant times the frequency. All right? So that Planck's constant h is also printed on the useful equation sheet. It is a number 6.626 times 10 to the negative 34. All right? And it's on the useful equation sheet. You'll be able to look that up. Nobody's going to expect you to memorize it. So we're in this weird in-between space where, for arbitrary reasons, we stick this limiting constant into the equation and things start to reflect reality. Next steps, done by a guy you may have heard about before, Albert Einstein. And he comes up, and we're talking in the 19 teens, so early 1900s. He says, hey, I've got a theoretical idea underpinning for all this stuff that we can start to put all this together as a coherent whole. He's studying what's known as the photoelectric effect. And the photoelectric effect is if you take a material, mostly at the time they were using a metal called selenium, you shine light on it, okay? The light can knock electrons off of the metal. But the way that happens is not what people think should happen. If light is a continuous wave, the brighter the light you shine, the more electrons should get knocked off. That's not how it works. It turns out if you want to knock these electrons off, the light has some cutoff wavelength. It has to be a short enough wavelength in order for the light to knock the electrons off. And the intensity of the light doesn't factor into it. And so what Einstein says is this is because the light is not a continuous wave, but it is coming as small particles, bundles of light, what we now refer to as photons. And that, in fact, the only way you can explain this is if light is functioning as a particle. And so now we've got this weird tension because some of our experiments, the only way you can explain them if light is behaving like a wave, and other ones you can only explain if light is behaving like a particle. Okay? And so this is known as wave-particle duality, and we're going to talk a lot more about that on Monday. But it turns out that the energies involved and the way that the light interacts with atoms is the perfect tool to begin getting a handle on how the electrons are arranged inside the atom. And we have this other new equation. This is the combination of the two equations I just showed you. We had C is equal to lambda nu, or wavelength times frequency, and we said E was equal to H nu, H times frequency. If you combine those two equations, you can relate the energy to the wavelength. Okay? This equation is not on the useful equation sheet. All right? They expect you to be able to derive it if necessary. Right? This is energy of a photon related to Planck's constant, the speed of light, and the wavelength. So, what we need to do, and what later on Einstein realizes, is that in addition to all this stuff, we begin to really fundamentally change what we think about energy and matter and how they're related together. Okay? That's what we're going to start talking about on Monday as we really dig into this fundamental shift in how we perceive reality called quantum mechanics. All right? For right now, here's what I want you to do. Okay? On the lecture notes, in the example box, I would like you to calculate what energy would a photon with 434 nanometers of wavelength, if the wavelength was 434 nanometers, what energy would that photon have? Grab a calculator, grab something to write with. This is the equation you want to use. Watch units. Watch out for units. Okay? So go ahead and take a minute. Take a minute. Calculate that energy. Pull out your useful equation sheet. All you need is a useful equation sheet. 6.626 times 10 to the negative 34. It's on the useful equation sheet. Pull out your useful equation sheet to look up Planck's constant and the speed of light. They're on the useful equation sheet. You should always have your useful equation sheet ready to go. Grab a calculator. What's the first step? Here's our wavelength, 434 nanometers. Right, what do we got to do with the nanometers? Can I plug that straight into here? Speed of light is in meters. So your first step. Remember, unit conversion stuff. Whatever units you're starting with, got to go on the bottom. Meters go on the top. What's the relationship between these? Printed on the useful equation sheet. Okay, remember, it's printed on the useful equation sheet here. Okay? Everybody should have a copy of the useful equation sheet. I gave you one a couple weeks ago. Yeah, hold on to it. Keep it someplace where you can always find it. You should always pull it out when you're doing work. Remember, on the useful equation sheet, the factor, that's the number that goes with the base unit. So it's the number of meters for one of the prefix unit. Okay, so on this useful equation sheet, for nano, what does it say? Ten to the negative 9. That's the number of meters to 1 nanometer. And that's on the useful equation sheet. You got to look that up. It's just the way they do this is the symbol. If you have one of the symbol, then the factor is for the no symbol unit. That's the way they print it on here. We are trying to figure out the wavelength in meters first. We're doing a conversion, converting nanometers to meters. So 4.34 times 10 to the negative 7. So that's just the pre-step, right? That's just the start so that we could take this and plug into this equation. So do that.
That's really cool.
C, the speed of light. It's on the useful equation sheet. Right-hand side towards the top. The right-hand side of the paper towards the top. That's also where Planck's constant is. Remember to use the EE button on your calculator. Times 10 to the. You gotta type the sig figs, the scientific notation in the calculator right. Why are you dividing by 434? Remember, we had to convert the wavelength into meters. That's C. Speed of light. C, the speed of light on the useful equation sheet. So what do we get?
Yeah.
4.58 times 10 to the negative 19 joules. So hopefully you're getting that answer. Make sure you're using the EE button to type the times 10 to the. That will cause problems. If you get like something not 10 to the negative 19, it's probably because of typing these times 10 to the incorrectly. Yep.
I don't know how I like just copied it, but I don't get how you copy.
I'm trying to convert 434 nanometers into meters. So every 1 nano is 10 to the negative 9 meters. So remember, the way you type this, 6.626, press the EE button. Put a little E on the calculator. Then negative 34. The E is the times 10 to the. All right? Then times 2.998, little e, 8. Divide by 4.34, little e, negative 7. It's the second function of the comma. Find the comma button. Look right above it. See the little blue EE? Press second in the upper left, second, and then the comma. See how it points to a little E? No, not times 10 to the negative 34. E is the times 10 to the.
Wait, how do I do the times 3?
Oh, this calculator is a little different. Let me see. On this one, where is the times 10 to the? Yeah, just going to do that. You might need to use parentheses on the bottom. For this kind of calculator, just for the numbers on the bottom, put it in parentheses. That'll help. Yeah, questions?
The equation where it says 0.66 times 10 to the 34.
Yeah. Oh, it says meters times seconds. That's a typo. Sorry, thanks. Yeah, it's joule seconds. Let me see. You did a power, and you're just literally supposed to type negative 34 after the E. No power, no nothing. The E is times 10 to the. And then you just type negative 34. So again, guys, real quick, got to get that times 10 to the step down. How do we type in? So 2.998 should have this E8. No power, no anything, just E8. I'm just, how do you type it in? What should it look like when you type it in? All right. We'll keep working on this. Don't worry, there's plenty of practice problems on today's active. Next steps. We're almost done. Let's finish this home. Because I'm recording a lecture. Whoever needs it. Yeah, that's what I got, right? I rounded to 3 sig figs, right? I rounded to 3 sig figs. All right.
You put it on YouTube? For anyone or just for school?
For anyone.
You make money? Average views?
All right. So now that we can figure out the energy, of a photon, next step, okay? Scientists, a couple of different guys looking at how does light interact with matter, okay? And so we've got our black body radiation, but there's another way that light can absorb and emit, or matter, atoms, can absorb and emit light, okay? Instead of just heating them up, we can, say, give them discrete amounts of energy by putting them in an electric field or bombarding them with electrons. This is sort of your classic sort of neon light situation, all right? And so a guy named Niels Bohr, a Danish chemist, is studying the results of this, what's known as spectroscopy, studying how light interacts with matter. If you take white light from a light bulb and you shine it through a prism, you get this rainbow effect, okay? But if you take something like a neon light, but instead of using neon, you put hydrogen in here. So you put hydrogen, high voltage electricity, and you shoot the high voltage electricity through the hydrogen gas. Instead of getting a full rainbow spectrum, you get only a very few, a small handful of individual wavelengths. Okay? So this emission spectra is what it's known as, is a unique fingerprint for each element. Each element gives you a different pattern of light. Okay? And what Bohr realizes is that what's happening inside of the atom every time it absorbs energy or releases it is an electron is changing energy levels. And what Bohr realizes is the only way that you can get this very specific pattern of only certain energy levels is if the electrons cannot be any energy. They can't be in any kind of orbit. It can't just be random. They have to only have very specific energy levels inside of the atom. So that inside the atom, the allowable places where the electrons can be, they could be at this energy orbit closest to the nucleus, or they could be at the next one away, what we call n equals 2, or they could be at the third one or the fourth one, but they literally cannot be in between. That the energy levels of the atom are quantized. That an electron will start as close to the nucleus as it can get, and when it absorbs energy, it jumps up. Okay? So the electron grabs energy and, hit by a photon, jumps up to a higher energy level. It can only absorb this exact amount of energy. And when it drops back down, it has to release that exact amount of energy, giving a very specific color or energy of photon that it releases. Each jump being a specific difference, a specific energy, a specific color or wavelength of light. Okay? Question?
Well, the electron goes through the process of
Yeah, we're going to talk about that on Monday when we start to talk about quantum mechanics. But what Bohr and Heisenberg and a bunch of guys like Einstein and de Broglie in the early 1900s, 1920s and stuff come to realize is that pretty much everything we think we know about how particles behave doesn't work when you get down to this scale. And the idea that you can say where the electron is doesn't make sense. And you can't do that. There is no defined location. And we're going to talk more about that on Monday. But we're not quite there yet. The initial Bohr model is the electron can be in this orbit or that orbit. How does it get in between? No clue. But don't worry about that. We'll talk a little bit more in a little on the edges, because to explain a lot of this stuff, you need sort of more advanced calculus skills than you guys have. Now, a couple of things to note. The spacing of these energy levels, okay? The spacing of these energy levels. And when we start to look at the colors and things like that, that they're not evenly distributed. And in fact, it's an exponential function that describes the energy that the electrons can have. I'm showing you the equation that Bohr came up with. You don't need to worry about this. It's not on the useful equation sheet. It's not on the test. What you do need to recognize is that the jump from the first energy level to the second is way, way bigger than the jump from the second to the third, which is a lot bigger than the jump from 3 to 4. Okay? In fact, this jump from 1 to 2 is so big that any electrons that are jumping either down into it or out of it have to involve ultraviolet photons, photons with lots of energy. Okay? Ultraviolet light has more energy than visible light, which has more energy than infrared, which has more energy than radio waves. So if you have any jump, 2 to 1, 3 to 1, 4 to 1, any jump down to 1 is ultraviolet. We can't see that with our eyes. Jumps that produce visible light that we can see with our eyes are pretty much confined to jumping into or out of the second energy level. So an electron that drops from 3 to 2 gives off a red photon of light. A little more energy to go from 4 to 2, you get a green photon. A little more energy to go from 5 to 2, you get a blue photon. Okay, 6 to 2, you get a purple photon. And after that, you're sort of at the edge of the atom for a hydrogen, and it's complicated. Don't worry about it. What I need you to know, visible light jumps are going to end in the second energy level. Okay? When an electron drops down, it gives off photons. When a photon goes in and hits the atom, it causes electrons to jump up. The electrons might start in the first energy level. They get hit by an ultraviolet. They jump up to n equals 5. They can do multiple hops down. They don't have to go all at one step. In fact, there's a lot of cool, complicated quantum mechanic rules about what jumps are more or less probable. Okay? Not something we have to worry about. Now, this equation, Z, is the number of protons in the nucleus, what we call the effective nuclear charge. And so for hydrogen, Z is equal to 1. And that makes this equation sort of quite a bit more straightforward. Okay? And when you start to say Z is 2 or 3 or 4, things get a little fuzzier. We'll talk more about that next week. This change, this quantization of the energy levels, turns out to be huge for how we think about the way that electrons are arranged in an atom. Because now we can think about and talk about, well, how many electrons can we put into each energy level? And that is what is going to drive all the chemical properties that we're going to worry about. Okay? And so we're going to dig into that next week. Today is about understanding the basics of electrons jumping, changing energy levels, and doing some calculations with light and things like that. But one of the cool things about all of this is this realization means that we can begin to understand and explain what is going on in fireworks. How do we get different colors? We use different elements. Different atoms have different spectra. They will release different colors of light. And so, in fact, you can detect and figure out what a substance is by looking at the light it gives off when you heat it up or excite it. Okay? So, sodium gives this classic yellow-orange color because of the way the electrons are arranged inside. Okay? Copper, you'll get this blue-green color. Okay? So you get these classic colors. And if you break it down and look at the line spectra, you can do this from billions of miles away. It's how we figure out what's in other stars. And even in the atmospheres of planets orbiting other stars. we can look for these signature colors and the specific frequencies of light that are emitted and detect compounds in distant star systems. That's a thing that we do, okay? So when you watch fireworks, every time you see a different color, you're seeing a different compound as part of the explosive matrix that heats up and emits light, okay? All of this is getting us to the point where we can start to describe where electrons are, how they're arranged inside of atoms, which will lead us into the properties of the elements that we want to describe. Okay? There is an active assignment for you guys to watch, or not to watch, to do. So an active assignment, you're going to have to do a bunch of light calculations. There's some questions about energy getting absorbed or released from atoms, all that kind of fun stuff. Yeah, that's it for today.